Hello and welcome back to a new episode of Plan C, Ocean Interventions to Address Climate Change. I'm your host, Anna Madlener, MRV Manager at the Carbon to Sea Initiative, and with me is, as always, my co-host, Will Burns, who's the Co-Executive Director of the Institute for Responsible Carbon Removal. Hi, Will.
Hi, Anna.
It's great to be back. We are kicking off Season 3 of Plan C, and this is its first episode. I'm really excited to be diving into a whole new set of topics and news and scientific research again with you over the next months. And I'm particularly excited to be kicking this new season off with stellar guests who are going to talk about a project that has been pretty much, I would say, years in the making, and it's been highly anticipated within the ocean alkalinity enhancement community. Will, what's in store today?
Yes, it's really highly anticipated. We're welcoming Dr. Adam Subhas and Jennie Rheuban, who are both from the Woods Hole Oceanographic Institution. Both of them are back after conducting an open ocean research trial off the coast of Maine in August as part of the LOC-NESS project. This was the world's first major open ocean alkalinity enhancement field trial, and it received approval from the U.S. Environmental Protection Agency, or EPA, under a statute called the Marine Protection Research and Sanctuaries Act after a rigorous year-long review.
Yeah, and as you alluded to, that permitting process was lengthy, it was rigorous, it was long. It included consultations with federal agencies, including NOAA Fisheries and the U.S. Fish and Wildlife Service, along with 2 public comment periods, which totaled 75 days, I think. And during this experiment, the scientists from WHOI introduced small amounts of highly purified sodium hydroxide, which is a compound that's also commonly used in drinking water treatment, actually. And they added this to the surface ocean to test OAE's potential for safely removing carbon dioxide. And so, yeah, we'll have lots to discuss. What are you looking forward to, Will?
Well, in addition to hearing at least some of the preliminary observations that they have about the science, I'm obviously interested in 2 topics that are near and dear to the heart of the Institute. One is their journey to obtain this permit under the MPRSA, and second of all, the issues of public engagement. How about you, Anna?
Mm-hmm. Yeah, that checks out. Likewise, those are definitely topics that I'm looking forward to talk about, as well as just generally hearing and sharing with the world what it took to pull this off. Those who've heard Adam or Jennie talk about this project and present plans for this project for 2, maybe even almost 3 years now, know how much scientific and engineering and logistical prep it took to pull it off. And so I'm looking forward to sharing that, as well as hopefully getting some glimpses at first results as well, and just hearing how it went, what happened. So speaking of, shall we bring them in?
Let's do it.
Hello. Hi, Jennie.
Hi, can you all hear me?
Yes, loud and clear.
Awesome.
Did you have a good vacation?
Yeah, we my husband and I went on a long weekend trip, which was nice, out to Western Mass.
Western Mass is nice. I spent a year there once as a scholar in residence at Williams, and looked all over Western Mass, and it was quite pretty.
Oh, wonderful.
Nice. Hello. Hi, Adam. Can you hear us?
Hello, yes.
Hi. Nice to see you. We were just chatting about Jennie's vacation, and we heard you went on vacation.
I did. I was in India for a little over 2 weeks, yeah.
Nice. All right. We have a lot to discuss, so we should stop talking about vacation. And let's kick it off. Welcome, Jennie and Adam. It's great to have you on. Great to see you. Thanks for joining us today. I would love to kick it up with just some personal introductions. Please tell our guests who you are, what brings you here today, and of course, talk about LOC-NESS.
Hi, Anna and Will. It's great to be here. And yeah, thank you for the invitation to participate and chat today. My name is Jennie Rheuban. I am a research specialist also at the Woods Hole Oceanographic Institution in the Department of Marine Chemistry and Geochemistry. I am here today because I have been working with Adam for the past couple of years as a co-PI on the LOC-NESS project. So excited to talk about our work today.
Yeah. Will, Anna, it's great to see you. Thanks so much for having us on. I'll get started. My name's Adam Subhas. I'm an associate scientist at the Woods Hole Oceanographic Institution. I'm in the Department of Marine Chemistry and Geochemistry, and I'm also the lead of the LOC-NESS project, which stands for Locking Ocean Carbon in the Northeast Shelf and Slope.
Awesome. It's lovely to have you both on. We already alluded to the awesome length and duration that this project has gone through a bit in our introduction. Folks have probably heard both of you talk about this project for quite some time. For those who have not, will you mind sharing just what the LOC-NESS project is about, the goals, and yeah, give us a bit of an idea of the journey you've been on?
Yeah, so the LOC-NESS project is a research program that has components of basically all aspects of oceanography, from chemistry to biology to engineering to geochemistry. And the project got kicked off in 2023, and we're approaching the fourth year of the project. And the center of the project is focused around field trial of ocean alkalinity enhancement in open ocean waters. But it's a whole lot more than that. So over the past 3 years, we've been conducting laboratory experiments, looking at biological responses and geochemical responses to ocean alkalinity enhancement. We have an ocean modeling team that's spent a lot of time understanding how ocean models can be used to track carbon and assess the biogeochemical impacts of ocean alkalinity enhancement. And we also have an engineering team that over the past few years has really been dedicated to practically understanding how to deliver alkalinity efficiently into ocean waters, and do so in a safe manner as well. And then finally, I'll also mention that we do have a significant engagement component as well. So we've spent a lot of time, as I'm sure you're aware, engaging with communities up and down the East Coast on the project, on ocean alkalinity enhancement in general. And the goals of that have been not only education, but also seeking feedback and incorporating that feedback into our project plan as well.
Cool. You already alluded to it, and before we go into a bit of the history and details around what went into this project, I want to make sure that our listeners know sort of the big milestone that you just reached and are sort of concluding, and now, sort of entering a new stage. So, you just came back from the field of actually doing that field trial that you mentioned. It is sort of the heart of this research effort. Can you just paint the picture of what did that look like? What did you do, so that everyone sort of knows what you work towards?
Yeah, so we just got back from conducting an open ocean alkalinity enhancement field test. This is the culmination, obviously, of years of work from our team, as well as hard work by regulators to actually issue the first of its kind permit for this project as well. That was issued through the EPA Marine Protection Research and Sanctuaries Act. And this experiment, as you said, is the culmination of a lot of hard work by this team, and it took a lot to pull off. What we did is we took actually 3 vessels from 3 different ports that converged on one place in the Gulf of Maine, the region known as the Wilkinson Basin, and we dispersed about 50 tons of alkaline solution into ocean water, and then measured the chemical response, so the transfer of alkalinity into seawater, or alkalinity enhancement. We deployed a whole bunch of sensors to try to measure the carbon uptake that resulted from that alkalinity enhancement. And then we also had a whole biological sampling campaign to measure biological responses to alkalinity enhancement from everything all the way down to the base of the food chain, phytoplankton and algae that fix carbon dioxide into organic matter, to zooplankton, and we even had protected species observers to look at larger marine mammals and other protected species that might have been in the area during the trial. So as you can imagine, a whole bunch of stuff that we measured after doing the dispersal, a whole lot of effort, including engineering effort, going into the dispersal itself. And now we have a lot of data to dig through and synthesize to actually understand in detail, right, how what all happened.
Mm-hmm. Awesome, thank you. And so one more final question before we dig into some of the permitting experience and what the research days look like itself. You mentioned that the project kick off early 2023, I think. Roughly, what did the preparatory phase throughout these last few years look like for you, and how did you go about planning this project?
Well, the project kicked off in 2023, but the idea really started when we first pitched a proposal to Carbon to Sea much earlier than that. As early as, I think, the idea was sort of formulating in late 2021 or 2022 even. And since then, it's been a journey of constant changes in project scope and plan, but all the while kind of centered on the fact that we knew we wanted to do a field trial as part of this project. That was a really critical piece, both from Carbon to Sea's perspective, but also us. We have the expertise, the in-water oceanographic expertise of doing science at sea, and that was a really important part to keep as the core of this research project. So maybe I'll leave it there and then hand it off to Jennie if you want to add some comments.
Yeah, absolutely. So one thing that I think is a point that I would love to stress here is that our research program has grown quite dramatically over time. So like Adam mentioned, we started with these initial conversations in 2022. We received our initial funding from Carbon to Sea in 2023 that was really focused on the execution of the field trial. And as sort of time went on, it became very clear that there were more aspects of the research program that we really needed to dig more deeply into. And so we started adding on additional components, additional collaborators. We have colleagues. There were several projects that were funded through the NOAA NOP, or National Ocean Partnership Program, through NOAA, that were really designed to expand the capabilities of the program, both to add on additional biological sampling and biological measurements, as well as the ability to deploy autonomous vehicles out in the field during the field trial as well. We brought on a fisheries biologist who has expertise in laboratory assessments of larval fish. We brought on, as a partner, the Environmental Defense Fund, who really helped us to further develop and execute our engagement activities. So the program, which really started out as a core effort at WHOI, really has grown quite dramatically to encompass a number of different organizations and entities.
Mm-hmm. I think that's also a really telling reflection of, I guess, the research field of ocean alkalinity enhancement at large. That shows how interdisciplinary it is and must be, and how even doing a purely scientific research effort requires a bunch of other aspects to consider. So I'll hand it over to Will, who surely has more questions about this.
Yeah, I'm obviously really interested about the permitting process and the journey of the LOC-NESS project. So just to set the table a bit for those that don't spend a lot of time in the esoteric world of U.S. law in this context. In 2024, the U.S. EPA issued a guidance document for permitting MCDR projects. And they essentially indicated that based on the methodology of the project, they could be regulated under the Clean Water Act or the Marine Protection Research and Sanctuaries Act, or the MPRSA. And the MPRSA implements the U.S.'s obligations under a treaty that we're a party to called the London Convention, which regulates the deposition of materials into the oceans and requires permits in most cases for those activities. The MPRSA was relevant here because obviously this project involved disposition of materials into the ocean and was under U.S. jurisdiction. And MPRSA here issued a research permit, which it determined had scientific merit that outweighed the potential effects that could result from the project itself. And so the first question I have is, can you explain what your biggest challenges were in obtaining this first of a kind permit under the MPRSA for a marine carbon removal project, and some of the modifications that you made to the project based on feedback from the regulator?
Yeah, so I'll just say, our conversations with the EPA started pretty soon after we were, made aware that the project would get funded in the first place. And so our conversations with the EPA actually date back to 2023 or maybe even late 2022. And at that time, it was still a little bit unclear where we wanted to do the experiment. So these conversations around, is it Clean Water Act? Is it MPRSA? We were having that same internal discussion kind of simultaneously. And this was obviously a huge learning curve for us as scientists to think about this research from a regulatory perspective, right? That's not a common way that a lot of us in ocean science think about our research. And it was also clearly new for the EPA to think about permitting, climate change mitigation or approaches that could potentially ameliorate environmental harm under this existing framework. So in terms of the challenges, the modifications, this was such an iterative process. And I want to give a lot of credit to the staff members at the EPA that we worked with, who were really they're scientists in their own right. They come to this problem with their own information and expertise. And it was a massive effort of iteration, of discussion, of narrowing in on key aspects of the project that were relevant to the regulations in place, that the final result of what we monitored for, how we did that monitoring, really came out of these deep conversations that we had with EPA staff. I'd say, some of the key things that are elements of the permit that we really had to think very deeply and carefully about in collaboration with the EPA were things like the dispersal monitoring phase. So how we monitored for pH thresholds and what conditions were put in place if certain thresholds were met or exceeded. All of that involved a lot of back and forth between us to understand, what our actual capabilities were, what made sense in terms of abiding by, water quality standards or water quality criteria, and what we could actually do practically in terms of in the field and changing dispersal characteristics. And the other thing were, all the decision making and contingencies around biological responses. So protected species, including protected species observing, what kinds of biological measurements we would need to make and report back to the EPA on. All these aspects were a conversation that we had with the EPA that ended up in the final permit.
Great. Yeah, one of the things you said at the outset, I think, is really important for people to remember, which is that when it comes to research institutes or it comes to startup companies, most of the time they're not going to have the luxury of a cadre of lawyers, right? And yet to navigate this process, one must engage with the regulatory process and maybe develop new skill sets on the fly. One hope I have is that, first of all, if there's any lawyers out there listening that have environmental expertise, this is an area that you can be really helpful, perhaps in terms of some pro bono help with companies and research institutes of this nature that need to be doing this. And then, second of all, of course, the fact that you were the pioneers in this field have provided us with some insights, and also EPA presumably will also be able to facilitate these kinds of permits in the future more quickly based on what they learned. And so my follow-up question is kind of related to that. What are some of the lessons that you learned from your experience in the regulatory process that you might share with other researchers or project developers that are looking at MPRSA or, Clean Water Act permitting in the future?
Yeah, I can take a stab at that one first. So I think one of the key things, at least certainly at the highest level, is to reach out as early as possible, even if you don't have a full idea formulated yet, just to really open that conversation and to understand who do you need to talk to, what are the entities that are going to be responsible for permitting the project, which groups do you need to speak with. For example, some of our early conversations were with the EPA Region 1 office, which is here based out of Boston, where we were sort of quickly directed towards their headquarters in DC, who did largely handle the permit application and our permitting process. But Region 1 staff were also still involved. And so, really understanding even just a quick question, who do I need to talk to? I would say as early as possible, people should reach out. Another thing that I was not aware of when we went into this process, and I don't want to speak for Adam, but I suspect most of our team was not aware of this, was the extent of the consultation process that this whole project would go through, and any MPRSA project would go through. For example, through the EPA, our project underwent consultation from maybe 4 different entities. So the EPA, as part of their work, does tribal consultation. So they reached out as part of the permitting process to regional tribes to connect and consult on their evaluation. They did consultation with NOAA for the Essential Fish Habitat and Endangered Species Act assessments. We also underwent federal consistency review through the Massachusetts Office of Coastal Zone Management, and the EPA sort of helped to facilitate that process. And so, I was unaware of that. As a researcher myself, I don't, again, like Adam mentioned, we don't typically go through the regulatory process in the same way for some of the projects that we do. And so this was something that was very new to me.
Yeah. Anything to add in that context, Adam?
Yeah, I mean, I think the other thing to highlight is that even though the EPA is a regulatory body, these are scientists with PhDs and they're very keyed into the science, and it actually was quite interesting because this was a research permit, right? The EPA really wanted us to defend the science itself, right? What is the research that we're doing? What are the questions that we're asking? What are the hypotheses? And how is this proposed project going to answer those questions while minimizing environmental harm? And at the end of the day, right, that is what the permit was issued for, was the research. And this, as you said, Will, this balance of the scientific merit, right, versus the risk to the environment. And so again, because the EPA scientists were coming from this whole different arena of how to do science, what that science is for, and who the science is for, it ended up just, helping us shape our own thinking around how we were doing this research and who we were doing it for. And I think it was a really important and critical process. Like you said, we also did have a lot of help from WHOI's legal staff in terms of navigating the permitting process. But at the same time, we did, it was me and Jennie and the scientific team who took on a majority of the permit writing and crafting. And I don't want to underestimate that too, because it was really critical for the scientists to be involved, especially at these early days when these projects are so novel, to have that like really granular scientific input and have that direct conversation between project scientists and the EPA scientists to make sure that everything is aligned in the final product.
Yeah, I think one really important point in there is I know a lot of times those that are trying to do these projects are frustrated by the regulatory experience, right? It's often long and stringent, but as you point out, one of the benefits of it is that it really does require you to focus on the rationale for what you're doing and the processes that are attended to it in a way that I think can often improve a project. Not to mention the fact that if one obtains regulatory approval, right, it sends all kinds of positive messages to potential investors and other regulators. So regulation, I think, it can stymie at times, but it also can help facilitate these kind of projects. And I think this was a real textbook example of that. So let's talk about the public engagement process in this, right? And so early on, this project encountered some resistance from a key stakeholder group in the proposed research area, which were fishers. Can you explain what their primary concerns were in terms of the project?
Sure, I can take a stab at that. So we underwent a very significant engagement process that took more than a year, largely, for us to really feel like we spoke to the groups that really were concerned about the work. We heard people's feedback. We were able to incorporate that feedback, and that process took a while for us to really implement. But I will say we largely heard a lot of very similar concerns across many different groups. So not just the fishing industry, but across a number of different groups who were worried about the project and its scope. A lot of those concerns were related to commercialization and scaling. So not necessarily focused specifically on LOC-NESS at our research project, but what ocean alkalinity enhancement might look like when it's scaled up to climate relevancy. That was really one of the number one concerns that we heard. We also heard concerns about the potential biological impacts, so specifically related to impacts on the zooplankton community and commercially relevant fish larvae. That was one that was really brought up largely by the fishing community. We heard concerns about higher trophic levels, so that meaning things like adult fish or marine mammals, turtles, other species that are higher up on the food chain. And we heard a lot of concerns about the spatial overlap of our project with other marine activities. And specifically, this was largely fishing as a major other user of the space that we were proposing to work in, but also this, our oceans are widely used by others like recreational fishing groups, the commercial shipping industry, et cetera, offshore wind development in the Northeast region. And so, we were hearing mostly those four concerns come up over and over again in our conversations.
I'd love to dive a little deeper on that and perhaps spend a minute on, understanding how you navigated those. I'm wondering if also for the bigger picture, you want to share a bit about what motivated you as scientists to work on this project, because I'm sure it's not an easy tension to navigate, right? As you say, there's the reality of ocean alkalinity enhancement is that we're still evaluating the efficacy and safety of it, but there is also a reality that, private sector activities are taking place and they're exploring it as an option. So how did you address that concern when it was raised, and how did you yourself also think about it?
Yeah, again, this just put certainly me and I think a lot of the project team in a position to really think deeply about who we were doing this science for, right? Being put in positions where your assumptions and motivations are challenged in that way, I think it was a humbling experience, and but at the same time, I think it really did motivate us to see this as an opportunity to have this research directly address some of these concerns, because as you say, there are commercial and private sector actors that are pushing marine CDR and specifically ocean alkalinity enhancement. And I almost see it as a duty for us as scientists to provide the transparent and rigorous evaluation of the effectiveness and impacts into some of these potential techniques. And I think that was underscored by these engagement efforts, because a lot of these communities do want to see the scientific data, right? They want to see it in different ways than we usually think about and present data, but they were very interested in the science. As a project, we have this unique position, I think, in this space, that we don't have any direct ties to CDR suppliers. And we've always been committed to open and transparent data sharing. And I think that that did come across in our engagement efforts, and I think it made a difference. I think the other thing that we were able to do, right, was we did have the flexibility, and this is, again, a huge thanks to our funders and our project collaborators. We had the flexibility to pivot and address some of these concerns and interests by these other communities in the project plan. So to give you some examples of what those are, we ended up expanding our biological assessments of the effects of ocean alkalinity enhancement from just looking at phytoplankton to looking at zooplankton, and specifically one species of zooplankton that's really, really important for the region, that has links to not only higher trophic levels like the endangered North Atlantic right whale, but also it's a key food for larval lobster, right? So it had a really key tie-in to a really big industry in the region. So, and that came out of us taking a hard look at data, having therefore really informed conversations both with the regulators and with the fishing industry, and coming out with a research solution that could address some of these key concerns. The other thing is actually our monitoring during the trial itself. We ended up adding on Newston tows that sampled just the upper part of the water to actually try to measure larval lobster abundances in situ. So these are just some of the examples of how we were able to take that engagement, take the feedback, and incorporate it into the research.
Yeah, Jennie, something you said is an interesting issue for me when it comes to public engagement that I think project developers are often surprised about, and I'm always interested how they address it. So, by definition, this was a very small project, right? With limited parameters and limited objectives. But as you point out, and we found this in the planetary engagement process and the ebb carbon public engagement process, one of the most important issues for the public beyond the site-specific potential impacts of the project is what would happen if this were done at a really large scale, right? And that's kind of a disconnect for researchers, right? Because you're now being asked to defend, global deployment of this approach, right? And yet your project is very small. How do you square that circle? How did you communicate with the public, since you identified this as one of the primary concerns that they had moving into this?
Yeah, I think one of the things that we really tried to do was position our project very carefully in in this broader marine CDR space, and really try to communicate clearly to groups what we were trying to do with this work. And like Adam mentioned earlier, this was really sort of trying to provide open and transparent data and fully assess the risks and the benefits of this strategy and provide that information to our regulators. So one of the ideas here is to provide the EPA and others with guardrails around any future regulation around what a marine CDR industry might look like. And I think that was really one of the key messages. The other was, of course, positioning ourselves, but really making it clear to these groups that we're not endorsing ocean alkalinity enhancement at this point. This project and WHOI more broadly, we are not for or against any particular marine CDR strategy. We're not for or against ocean alkalinity enhancement, but we're really trying to do this assessment and provide this independent research for that. Adam, do you have more you want to add there?
Yeah, I think one of the things that Jennie, what you said is we made it very clear what this project is about, but we also made it pretty clear what the project isn't trying to do. And I think highlighting both of those things was important. And as Jennie said, we had a project design. It was designed to answer very specific scientific questions. And one really key thing that we tried to make clear in our engagement is that what we're doing shouldn't necessarily look like what scaled ocean alkalinity enhancement is going to look like. And those are very different things.
Did you get any pushback in that context? Did people say, "Look, what's the point of doing these small scale experiments if we're not potentially contemplating doing it on a large scale? So we want to know about what that would look like." Or did people accept the narrative? Right.
I will say people were very interested, even for our small scale experiment. Is it carbon neutral? What's the life cycle in terms of carbon emissions associated with our experiment? And that has very clear links to what a similar deployment might look like at scale, right? Very interesting question. It's something that we actually haven't really taken on as a research team as part of this, but is clearly just going to get more and more important, especially as carbon credits, right, start to get issued. But I think because of our position here, that we're a research team, we don't have any direct ties to the industry, and we made it very clear that we're in it for the science. I think we were able to, very honestly stick to that narrative, and people took that at face value. I think because of our position in the field.
I think it's also a tension that we generally, or that the OAE field is facing, right? There's sort of these opposing realities of the promise or the potential of OAE is that it can leverage the ocean scale and natural mechanisms, but therefore this idea of scaling it up is often used as one of the arguments to do OAE, while in reality, all of the projects that we are seeing actually testing this in the water and likely feasible deployments or efforts from an infrastructure perspective also are going to be much more local. This is going to look very different in many different places. It's always going to be very site and very feedstock dependent, etc. And it has so many different sort of faces, and so it's one of the challenges, I think, for OAE at large to break that down a bit and share how small research projects like yours help evaluate scientific hypotheses, but they don't sort of translate linearly to, okay, now it's going to happen at big scale all over the place. Let's dive into the actual experiment that I'm sure people are super excited about. Just generally, I think, obviously, everyone knows you're going to have a lot of data analysis to do. There's going to be papers written. There's going to be presentations given. What would you most like people to sort of know at this point in time about the time you spent at sea? What did it feel like finally going out there after 3 years of prep? And how did it go?
Well, I'll just say the 3 years of hard work preparing for this really paid off, because it really could not have gone more smoothly than I think it did. And that's a testament to, I think, everyone's hard work that went into every aspect of the project. The ships arrived in port several days before we even left, and a big part of our efforts leading up to the dispersal were preparing the vessels, right, to actually do the dispersal and do the monitoring. We typically bring all of or a big chunk of the instrumentation on board, and we had to sort of set up the lab from scratch to make the measurements that we needed to make. We also had to do a bunch of welding and loading and bringing on pumps and everything for the dispersal vessel to be able to actually conduct the dispersal itself. So that was a huge effort as well. Just in terms of how we felt, I think by the time the trial came around, I think most of us were really excited to just do it. I mean, it had been so much work leading up to it that I think we were all really, really excited and ready for it to happen. And, like I said, this actually involved 3 different vessels leaving from 3 different ports, all converging on one place in the ocean in the very early morning. And it was pretty incredible to have that all happen and all the vessels be there. It was really foggy that morning, and then all of a sudden the fog lifted and you could see all the vessels there in the middle of the ocean, and it was like, okay, like we're doing this, it's happening.
Would you have been able to do it if the fog hadn't lifted?
Yeah, we could have done it. We couldn't have gotten the remote sensing and drone imagery necessarily, but yeah, we would have still gone ahead and done it. Yeah.
But the weather felt it.
Yeah,
was
no,
ready.
yeah, we the weather was great. We had a weather window for ourselves, but we managed to get out right on the first day.
Okay, and so then that first day, you did the rhodamine dye and the alkalinity dispersal.
Yeah, we, actually, I'll just say, to add on more complexity here, the field trial, the dispersal occurred on the 13th of August. But really, our measurement campaign started well earlier than that. So we had a fleet of autonomous vehicles that went out several weeks before the field trial actually occurred. So they were deployed. One glider, which is a type of vehicle that sort of flies up and down in the water and has a sensor package installed on it, was deployed several weeks before the field trial occurred. Another one was deployed about a week beforehand, or several were deployed about a week beforehand. And then we had another autonomous vehicle that's a little bit more nimble that was deployed the day before. So it wasn't actually just the field trial and the monitoring phase with all 3 vessels converging on the site, but we had a number of assets in the water already there that were collecting background information and sending that data back to us in real time so that we got a sense of what the field site looked like and some of the characteristics before we were even out at sea. And, how it felt, I'll just say, again, I can't speak for Adam or the rest of our team, but I got almost no sleep the night before our dispersal. So we departed, the science team departed the WHOI dock on sort of the evening of the 12th of August. And, we had a little bit of setup and sensor testing to do as we were transiting. And then sort of everybody went to sleep or tried to go to sleep. I got almost none, both excitement, but also nerves about making sure that we really executed the dispersal properly and everything went smooth. So, it was exciting, also very nerve-wracking at the same time.
I bet. Yeah. And then you stayed out there for 7 days with 2 vessels.
We were out there for 4 days fully with the monitoring vessel only. So the way that the sort of field trial worked was that all 3 vessels converged on the same site on the day of the dispersal. We initiated the dispersal with the vessel that was carrying the alkalinity and the alkaline solution. The dispersal took about 6 hours or so to complete, and then that vessel that was carrying the alkalinity went back to port, and the monitoring vessel stayed in the field site following the alkalinity patch for 4 days afterwards.
Okay. And so for the MRV nerds like myself, obviously one of the super exciting outcomes or things that we're looking forward to from this research is information about whether you can actually trace and track and measure carbon removal. Anything you can already share on that, or just sort of highlight in terms of the hypotheses you were trying to test and early indicators you got, if you have them?
Well, let me start by saying, part of this too is just on the alkalinity side, knowing that, you add so much material to seawater and you see a certain signal in the dissolved alkalinity as a result of that addition.
Mm-hmm.
So that's one aspect of the MRV process, right?
Can you say more? Sorry, why is that not like, it might be, obvious? Well, you told us that you add alkalinity, therefore you will measure it. Why isn't that a given?
Yeah, well, so for our case, we were adding sodium hydroxide, so liquid, right? It should easily mix into seawater. But you still need to demonstrate that, right? I mean, you can demonstrate it in the lab, you can demonstrate it in a big tank, but you have to demonstrate it in the ocean if you're going to convince anyone that this is actually a real approach to carbon removal. And so it is on all of us. It was certainly on us, but it's on every project, right, to demonstrate that you add this much material and you get that much alkalinity into seawater. That is absolutely the first and most critical step in this process, and it needs to be demonstrated. And it's certainly even more important, right, for the mineral-based approaches where those minerals have to dissolve to produce the alkalinity. That's a slow step.
Yeah.
And it also potentially involves secondary reactions and reactions that could consume any alkalinity that does get produced. And that was a concern for us too, just because when you add sodium hydroxide, you can get other minerals precipitating. So that was a big thing that we wanted to document. I will say, roughly right now, we don't think that was a big loss of alkalinity transfer into seawater. So our data is currently suggesting that process was that loss term is really minimal, which is great to see. And then, right, we have this patch of rhodamine and alkalinity enhanced seawater that we tracked around for 4 days, and we used a whole suite of carbon sensing instruments to try to actually directly measure what happened with the alkalinity enhancement, how it dispersed and diluted with surrounding seawater, and could we actually constrain the carbon uptake as well? The alkalinity enhancement itself, right? Alkalinity goes up. That comes along with an increase in pH and a drop in the partial pressure of carbon dioxide or the concentration of CO2 in seawater. And we saw that immediately. Actually, the region of the ocean that we were in was maybe a slight carbon source to the atmosphere before we did the dispersal, and we turned it into a sink, and we could clearly see that in the CO2 data.
That's awesome.
Yeah, and it's like a beautiful signal, right? It's just like crystal clear. And so I think, already have the data in hand to show that these early stages of ocean alkalinity enhancement work exactly as people have said that they work and have shown to work in labs and mesocosms, et cetera. That's great. The next question is, can we actually observe the CO2 uptake itself? That is something that's going to take a lot of work. But again, all the preparation that we did leading up to this has suggested that we have a shot at measuring it, and we're going to be digging hard into the data to actually pull that signal out. I'll also say that we did do, as part of the preparation for this experiment, a dye-only tracer experiment where we just added rhodamine but used all the same sensing technologies to look at the carbon system. And that really gave us a methodology to apply to these kinds of data sets to be able to extract that signal. So we have deployed the right technologies, and we have the framework for extracting that carbon uptake signal directly out of this data set. And that's our job for the next few months is to spend the time, quality controlling all the data and then working on actually constraining carbon removal from this project.
Can I double check on that just to make sure I understand that correctly? You're saying that basically the first time you just added the dye and you tested a specific path and constellation and frequency of all of your equipment, of platforms, of sensors, etc., and basically had them do exactly the same thing than you later then did when you also added alkalinity. And because you had them do a specific path A and then again a specific path B, you can extrapolate that data, or why did one experiment exactly help you do that sort of extrapolation? And what would you recommend others also sort of taking from that and learning from that?
Yeah, I would say, we even built on what we did the last time. So, we had, on that first experiment, we had alkalinity and PCO2 and rhodamine sensors on the ship, and we added pH as another measurement to constrain the carbonate system, just as an example of something that we did. The really key thing about measurement of carbon removal is this concept of additionality, or being able to attribute a carbon uptake to the intervention that you did. So one of the really key ways that we were able to do that, right, was by essentially labeling the alkalinity with rhodamine. And that's a really clear way to distinguish between waters that never saw alkalinity versus the waters that we added the alkalinity to. And then it's a question of how do you do the differencing and the comparison with those waters that never saw alkalinity. And that approach of essentially driving the ship through the patch, sampling the patch itself, and then going outside of the patch and making sure that you collect samples outside of the patch, and then coming back through and basically doing this zigzag pattern constantly inside and outside of the patch gave us the ability to do this differencing continuously throughout the entire experiment, right? So we always have an outside the patch reference frame to compare to. And that's the really critical bit that is going to let us always reference to waters that have never seen alkalinity and always be able to do this. This is what the CO2 uptake was at the same exact time, relatively same place, without alkalinity and with alkalinity, and then we can do the difference and actually calculate the CO2 uptake.
Right. Okay. You meant it as a comparison sort of between not having alkalinity and adding alkalinity. That makes sense. One of the key advantages of your research setup was that you were in a region, as far as I know, and added the alkalinity in a way that was concentrated in this patch for quite some time. I think you said 3 or 4 days. There are obviously other approaches where the alkalinity disperses much faster. What do you think are some of the sort of advantages and extrapolations maybe from this experiment also that will have insights and meanings for these other approaches in the future?
Yeah, I mean, I think part of it was that we just wanted to be able to show that you can actually measure these signals. I think a lot of the assumptions going into a lot of these trials were that you can't.
Mm-hmm.
And I think we absolutely should be trying to measure the alkalinity enhancement and the carbon removal directly with instruments as long as we possibly can. And we should constantly be pushing the boundaries of our abilities to make those measurements. It's going to improve the technology, and it's going to improve our understanding of how the system works and our confidence in being able to assign a carbon removal amount to these early projects. So just fundamentally, like philosophically, I think it's important for us to be saying that, like, no, yes, you can do this. And we should absolutely be trying to in every possible circumstance. So that's the first thing. And then the second thing is, like, as I mentioned very early on, we do have a modeling team as well. And so part of the exercise moving forward is for us to compare the in-water data with our models and make sure that the models are actually giving the same result and that they are intercomparable. And that's a really critical piece because right now, a lot of the MRV credit issuance and registry protocols are based only on models for the carbon removal. And it's going to be really, really critical for these early projects to dedicate the time, the resources, and the energy into validating that those models are actually telling the truth about how much carbon is getting removed from any given project.
Yeah, I understand the efforts to measure the removal of carbon from the ocean. Does the project have implications or aspirations to then measure air-sea flux exchange, or is that beyond the scope?
Yeah, I was just going to mention. So we have instruments that will allow. We had instruments out installed on the ship that will allow us to calculate the air-sea exchange of CO2. So we have in-water measurements of the partial pressure of carbon dioxide. We have in-air measurements of the partial pressure of carbon dioxide. We have wind measurements, and from that series of measurements, we should be able to calculate the flux of CO2 in real time from the atmosphere to the ocean. Both in the patch where we, like Adam mentioned, we saw a pretty substantial signal and drop in the partial pressure of carbon dioxide by more than 300 parts per million. So it's really quite impressive. And from that, we should be able to calculate it. We didn't have instruments installed on the ship that would allow us to do, let's say, a direct measurement, such as an eddy covariance measurement. We didn't have that installed, but we should be able to calculate that from the series of measurements that we collected.
Yeah, just explain this to somebody who's a bit of a layperson on the science, right? My understanding from a lot of the things I read was that when we're calculating air-sea flux exchange, there's often a temporal element, right, that it occurs well after the intervention, and a spatial element, right, that's far abreast from where the initial intervention happens. Is that not correct?
No, that is correct. So you're going back to the question or the comment that Adam made about how it's going to be difficult for us to quantify the CDR fully in real time from our measurements, the carbon dioxide removal directly. So the challenge with the sort of CO2 uptake and the carbon dioxide removal calculation is that the exchange of carbon dioxide from the atmosphere to the ocean is relatively slow in the time scale. And so that means that we won't be able to measure the full signal. It's not all going to happen in 4 days. It is going to take some time as this patch spreads and dilutes for that CO2 uptake to happen. And so that's really the big challenge about the question, can we quantify the CDR carbon dioxide removal that's actually happening associated with this project? That's why Adam was mentioning that it's going to take a lot of digging into the data. It's why we're also, comparing with our model estimates. We were only out in the field for 4 days, so there's a limit to what we can really say from our measurements. But we're hoping, based on the conditions that were set up at the field site that we went to, we have a fairly strong chance of measuring a CDR signal, albeit it might be small. We have a strong chance of measuring some CDR that happened during those 4 days.
Great, thanks.
And I think Adam also raised an important point about sort of the way that quantification in early crediting right now is done, which is largely reliant or in terms of actually putting a number on CDR, it's entirely reliant on a combination of models. But what you laid out, I think, is that we can sort of, I think, bring this message home a bit more, that the model is only or should only be sort of the last step in a series of proof points and steps to sort of provide this evidence that, yes, you did indeed add alkalinity and you increased alkalinity in the ocean to the extent that you thought you would, given this amount of alkalinity. And then secondly, that you did indeed measure the fact that the partial pressure of CO2 dropped in the water, which is the second crucial step after adding alkalinity to even give the ocean the chance to draw down more CO2. And then this last bit of the actual drawdown is probably where, if you see that signal from the measurements, that would be awesome. But also all of the steps you took before that will allow you to validate those models and build that confidence that a modeled CDR estimate could indeed be correct. Correct me if I'm wrong here and sort of laying it out like that. But I think it's a really important message in talking about MRV for OAE, that there are these different tool sets that we have in order to build that confidence.
Absolutely. I think that's really well said.
So I would love to close on just laying out what comes next for your team. I mean, the trial happened, but as you alluded to, the project is not finished. Now comes a new set of hard work. What's sort of the timeline, and what should our listeners be looking out for, and how can they stay up to date with what you're doing?
Yeah. So, events like this, podcasts, et cetera, we'll be trying to get our message out when we can. And we'll definitely be providing hard data when we can and when it's available. Stay tuned for the Ocean Sciences meeting in February. I think we have 12 submitted abstracts from this project on basically every aspect of the project. So definitely stay tuned for that. We're also planning on circling back to the communities that we engage with and getting information back to them too. So that's another really critical part of our information sharing. And then we also regularly post updates on our project website, papers submitted in press, published, and any news stories that come out. We try to get those up on the website too, so check there as well.
Thank you so much for joining us. It was a really insightful episode. Fantastic way to kick off season 3, and we look forward to talking to all of you more over the next months. And as always, thank you to our listeners for joining us. Stay tuned for everything that's to come in season 3. Goodbye.